start. Today we're going to be back to the problem of mechanical vibrations in a 1D chain, and we'll do the quantization, essentially how to treat the problem quantum mechanically. So from now on, all the fields that I'm writing are quantum operators. You have to worry about commutators and so on. Okay, so this is elastic vibrations in 1D. And let me remind you where we arrived at the end of the previous lecture. So first of all, that you can write down a field theory for the local displacement of the chain at every point on a line x. So x is a continuous coordinate, and there's a local momentum. And when we quantize these fields, they become non-commutative objects which obey the following commutators. For coordinate and momentum at two different points, x and x point, we get IH bar times the Kronecker delta, the Dirac delta, where the way we got this, I'm just reminding, we use the fact that in the discrete version, where the displacements are attached to specific atoms, okay, this is how we started the problem. We started from a discrete chain of masses on springs, and we had an index n for each mass. And then you know that just like in standard quantum mechanics, each particle has a coordinate and momentum, and they are obeying canonical commutation relation. But when we go to the continuum limit, using the fact that basically we can take the limit that the lattice spacing, which gives the discretization, goes to 0, Kronecker delta divided by A gives you a well-defined continuous function. Actually, it's a very ill-defined function. It's the delta of Dirac. Okay? But this is the quantization of the field. And in terms of these fields, the Hamiltonian has the following form. It's an integral over x of the local Hamiltonian. Okay, and the integral goes from 0 to L, where L is the length of the chain if it's a finite length. Today we're going to keep it finite just because we need some normalization there. And the H is represented by kinetic energy, which is pi square over 2m plus the elastic term, which has the stiffness parameter, gradient phi square. Okay, that's where we arrive. And now I'm not putting hats on the quantities, but these are all quantum operators. And in the Hamiltonian, pi and phi are non-commutative objects, so that's why it's a quantum, a non-trivial quantum operator. Okay? Now, so this theory is relatively simple. We saw already that if we derive equation of motion by minimizing the action. This is what we done last week. We get a linear equation, just a wave equation, standard wave equation. We also realized that there are two parameters in this theory: the mass and the stiffness, elastic stiffness, and combination of them has units of velocity, and that's the square root of rho s over m is a velocity that describes the velocity of the propagating waves in the classical wave equation. But we'll see today how it comes about. It really describes the velocity of propagation of some modes, some kind of degrees of freedom that are going actually to replace the original atoms. So let me first, before I do mathematics, just explain the strategy of what we'll do today. I remind you that we started from a problem where we had atoms connected by strings, so that the theory that describes them is not local. It knows about, it accounts for interactions between the particles. Therefore, they don't behave like a free gas of ideal gas. You can separate the particles. And therefore, the description in terms of the original atoms is not useful, it's not convenient. So we are looking for alternative degrees of freedom that will behave like particles, but in terms of these new particles, these so-called emergent particles, which are coming out of the interactions between the atoms originally, the system will become something that you can write as an ideal gas of some group. Okay? And this is what we're going to show today. The first step is to realize that we can make the theory more easily tractable by going first to Fourier space for both functions phi of x and pi. Because, and why is that? Because if we look at the potential energy is dependent on the gradient on phi and not on phi itself. So, and in Fourier space, a gradient will just give us the power of the Fourier component. So, so let us do it. What I'm doing is now defining the Fourier transform fields of both the displacement phi and of pi, and I write it like this. So I write phi of x as a Fourier expansion. Okay. And similarly I do for pi. But notice that here there's a little bit of difference. So I have some freedom when I write a Fourier expansion to make the exponent positive and negative. I want to keep the phase of the pi expansion opposite side. Why? You see that for convenience it will be better to write in this way. Okay? And phi k and pi k are now going to be the Fourier components of the local field. And if we invert this transformation nicely, I can explicitly write, sorry, and here I forgot something important, which is a normalization factor. Sorry about that. So let me write it. Okay, that's actually why I wanted to keep the boundary fixed with a finite length. And then phi of k will be 1 over n to the half integral dx of phi e to the minus I kx, and phi of k is integral of phi to the plus I. Okay, great. And now notice that phi and pi are non-commutative, and they obey this non-commutation relation. We can use this expansion to derive commutators for phi k and pi k, because obviously phi k and pi k are also not commuting, right? So we just plug in this expansion, and then we get, let me write it here. Now you'll see why I insisted on having an opposite sign here, because what we want to get is if I take phi of k and pi with some different k prime, this will give me IH bar times the Kronecker delta of k. Okay?
You're assuming that momentum is quantized, right?
Yeah, so, yeah, thanks for, this is something I wanted to mention next. Notice that in my original expansion, I wrote it as a sum over k. Now you may want to ask why sum is not an integral. So, in fact, if you have a finite length, okay, not every k is allowed here, right? Because you have some boundary conditions, and phi of x has to obey the boundary conditions. At the moment, it doesn't matter what kind of boundary conditions, because we are always interested in the thermodynamic limit if A goes to infinity. So it can be a vanishing boundary condition, or it can be periodic boundary condition. If you think of this chain to be on a ring with closed in a closed loop, then you have to identify 0 with L, and that's a periodic boundary condition, in which case the allowed values of k are 2 pi over L times an integer, okay, where j is 0, 1, 2, okay? Actually, sorry, it can be also negative, so integer. Okay? This is something you're familiar with. But actually, we just keep it this way for having everything well defined. But we know that eventually, most of the times, we'll be interested in the thermodynamic limit where L goes to infinity, and then this sum over k can be replaced by an integral. Okay, but that's a technical point. So the sum over k encodes all the allowed k vectors, or wave numbers, if you like, because it's in 1D. And they can be a continuum, they can be discrete. This depends on the boundary conditions, okay? Okay, but in any case, whatever they are, so let's assume that they are discrete, then indeed K and different K and K prime are commuting, but if you plug the same, for the same K, phi of K and pi of K are canonical conjugate non-commuting variables, okay? Okay, so very good. So let's take now this Hamiltonian and rewrite it in the in terms of the new field, and we simply plug in these expansions. Okay, that's all, and then we perform the integral over x, and when you perform the integral over x, you get some delta, right, which gives you eventually just one sum over k. So I'm not going through the calculation. I encourage you to do the steps on your own. It's a very, very useful exercise. But eventually what you get is the following expression. It's a sum over k of first term is 1 over 2m pi k pi of minus k, okay, plus sorry, I need pi k pi minus k plus 1/2 rho s k square phi k phi minus k. Okay? Let me explain something. First of all, why do we get here k and minus k? So if you do the calculation of this plugging expansion for pi, for example, let's take the first term, it's easier. It's a double sum of k and k prime. But then you have these exponents, and after integration over x, I'm basically using the fact that the integral of e to the plus or minus, doesn't matter, k plus k prime x, this gives you delta of k minus k. Okay? So that's why you get in the combination k minus k. How did I get this factor of k? Just exactly because it's a derivative. In k space, it becomes just ik times phi k, right? So that's how you get it. And the next thing that I want to do, just to rewrite the second term more nicely, notice that here there is the parameter rho s, and there is also a parameter m of the mass, and the ratio between them gives me a velocity. Okay, so I can rewrite the coefficient, this coefficient, I can rewrite it as okay, m omega k over square, where what is omega? Now I'm defining omega. Omega k is this velocity, which is the square root of rho s over m times k. Okay? So if you like, at this level, it's just a definition, because if I take a wave vector multiplied by velocity, I get frequency, right? Yeah, you wanted to ask something?
Yeah, this is the linearization of the bi-frequency, right?
Yeah, but already our theory is just that.
Right.
And you see it comes up. Yes, you are right. We made here, what we made here is essentially a gradient expansion, or we made an approximation to get this gradient in the first place, okay? Which is, taking the limit that the lattice spacing is small as we went to the continuum limit, and the fact that we have a quadratic dependence is harmonic approximation. And this relation between frequency and wave number is nothing but the dispersion of the waves, the solutions of the wave equation we just discussed last week, right? So you see, we can actually rewrite the elastic part of the potential energy as m omega square. And this form should remind you of what? What does it remind you? If it reminds anything. Yeah, it reminds of an harmonic oscillator, but with some twist or some complication, which we'll resolve soon. Notice that, and I will soon remind you of the harmonic oscillator that you know from undergraduate, because this will be our first step to understanding what I'm doing today. But notice that here, it's not just some pi square and phi square, but there are two fields, there are two distinct fields, pi k and pi minus k. Okay, and the same for here. So these terms are quadratic, but they are mixing the k and minus k components of each field. Okay? Now it must be like that because of the following thing. Now remember, phi and pi of x are nothing but the continuum limit of the original phi n and pn, which are coordinate and momenta. These are physical operators that, in terms of, or physical quantities, that the quantum operators of them are Hermitian, right? You remember that any measurable, observable, any physically measurable quantity, when you quantize it, it must be a Hermitian operator, okay? So phi of x and pi of x are Hermitian. But what about phi k and pi k? They are not Hermitian. Why? Because there is an I here, right? So phi k dagger, what will be phi k dagger? It will be, phi is still, phi dagger equals phi, but the conjugate of this is plus, right? So this is actually a mathematical statement about any field that in real space is Hermitian. Its Fourier transform always obeys that phi k dagger equals phi minus k, and the same is true for the momentum. the momentum pi, exactly the same story. The dagger of pi, or the conjugate of pi k, is pi of minus. Okay? I emphasize that it's not always true, it's only true if in a real space the fields were real. Okay? Otherwise, there's no such symmetry, right? So this is actually something very useful to observe. And it actually suggests that there's a different way where I could write pi dagger pi x, right? Which already should remind you of something, right? If you remember from the harmonic oscillator, if you write it in terms of ladder operators, it's something like A dagger A, but here we still have two different fields, phi and pi, and they obey some commutators, which are the canonical commutators. So it's not exactly, but everything points at the idea that we should we should treat this problem, if you want to get something really simple, similarly, or in fact almost identically to what we've done for a harmonic oscillator. So here we don't have just one, we have many modes, okay, maybe even the infinite system, but each of them brief review of harmonic oscillator from undergraduate, and there's something conceptual in that problem that carries on to field theory of a many-body system. Okay, so harmonic oscillator. Just for a single particle, so I remind you we have something like a quadratic potential as a function of x. This is x. This is v of x. Okay? And we write the Hamiltonian as p squared over 2m plus okay, so this is the potential, which we call k, if you like, and okay, just a single degree of freedom. It's a single degree of freedom, and x and p. Don't confuse it with our x, which is just a coordinate, a static coordinate. Here, x is a dynamical particle, okay? But don't get confused by it. Try not to, okay? Okay, so this is what it is. Now, to get essentially, so we know that this problem is one of the prototypes that you can solve exactly, and we know and love, and we try to approximate anything by it. And to get all the spectrum, you can use an algebraic approach, right? You don't necessarily have to write it as a differential equation. You can, of course, because the first term is a gradient square, and okay, you can solve an equation which is called the Weber equation. You get some Hermite functions and all that, but all the physics, the essential physics, can come out of an algebraic approach, which gives you the spectrum and, in fact, a way to compute any observable, okay, in a very convenient way. And the idea is to introduce here ladder operators. And the motivation is that you see that x and p appear in the Hamiltonian in the same functional form. Both of them are just a square, right? So it's very tempting to introduce variables which combine them to get just one quadratic thing instead of sum of two, right? And that can be done by introducing the so-called ladder operators, A and A dagger. So A is I'm writing here a definition that I will soon define what is L. Okay, so L, okay, there's a length scale here given by some combination of the parameters, which has units of length. And that's why I'm writing it like this, because you can see just from the first term and also from the second that what are the units of A. I mean, in terms of physical units, it's dimensionless, right? Because you are normalizing everything that has units of length by 1 over A, okay? So this is A, and because X and P are Hermitian, but in this linear combination there's an I. A dagger is not the same as A, it's X minus I, A squared over H bar, okay? And one can easily show that the Hamiltonian can be rewritten in terms of these A's and A dagger, giving H bar omega A dagger A plus a half, right? And I'm not explaining, I don't get it, because I'm assuming you all know it, I just repeat. And there's, in order to get this half, actually, what I used is, I used the commutators of X and P, and if X and P obey the canonical commutators, one can easily show that A and A dagger give you 1. Okay? So there is an algebra here of these operators A. A and A dagger are non-commutative, and on the right-hand side is 1. And of course A commutes with itself, and the A dagger commutes with itself. I don't even have to write it. But when you have more than one A, you have to keep track of it. But for the moment, this is all we need. And keeping track of these commutators, you see that in the Hamiltonian there's some constant here, and there is something times A dagger n, and this something, what is it? H bar omega.
Energy.
It's some characteristic energy proportional to the frequency with H bar, and the beautiful thing about it is just from this form we can get the spectrum, the energy spectrum of the particle in the harmonic potential, and see that it has a very unique property. What is this unique property? That the spacing between adjacent energy levels is constant, and it's h bar omega. Okay, so how do we know it? We know it because laser. Okay, let me erase this. So, we see that actually we can define a ground state of the system, and we know that it must have a ground state because it's a positive definite potential, and all energies must be at least zero, right? So there is a ground state, and the ground state is something that obeys, if you apply the operator A on it, let me just write it here again. Okay, this is what it is. Sorry for erasing. So applying A on the ground state gives you 0. Okay, so there is a ground state which is an eigenstate of the operator A with zero eigenvalue. Okay, but if you apply a dagger on A, on the state, on the ground state, you get a state that I call 1. Why is that? Because the combination A dagger A acting on the state that I will call now n is a number. Okay, so there is a ladder of states which are eigenstates of the operator A dagger A with an integer quantum number. So the operator A dagger A is a number operator that counts how many times we are moving in the ladder. And if we start from the ground state and apply A dagger again and again and again each time, and of course you put some normalization factor to ensure that you get a normalized wave function at each point, you get a spectrum of energy levels that looks like a ladder. Okay, so if this is some space. So this was the harmonic potential. I have a ground state. And then let me use here some colors. This is E1. E2. And so on. So the spectrum is just an equal spaced ladder where the energy difference between each state is just h bar omega. Okay? So in other words, this Hamiltonian, which I wrote here, let me re-express it in the following way. There is some ground state energy, E naught. At the moment, it's actually half h bar omega, but the moment I don't care what it is, there's a ground state energy plus some constant quanta of energy, which happens to be h bar omega, times A dagger A. Okay, that's the form of the Hamiltonian. And epsilon is indeed h bar omega, but what is important to notice is that it's a constant, okay? So A dagger A, its eigenvectors have an eigenvalue n. It just counts how many times we moved up in the ladder, and therefore the spectrum, what is the spectrum then, is just okay, so this gives you En equals E naught plus h bar n. Okay? Okay. So having this better in mind, we can interpret the operators A and A dagger. A is the operator that takes you from one level down to the next, right? So it's a lowering operator. And if you apply it on the vacuum, what happens? You just get 0 because there's nowhere to go. Whereas A dagger is a rising operator. And you can apply A dagger again and again. And each time you're adding the same quanta of energy. Okay? And you get a state, let me write an expression for the state n, which is, there is some normalization factor, times A dagger to the power n acting on the ground state. Okay, this will be a state, a normalized state, which is an eigenvalue of A dagger A with eigenvalue n. Okay? Okay, this is just, is that familiar to everybody? Okay. Good, okay, so now, so this is mathematical, if you like, it's a mathematical trick that allows you to get the spectrum and to write the Hamiltonian in a compact way. But there is also a conceptual idea behind it, because notice that these raising and lowering operators, I could interpret them in terms of the emergence of a new particle which is related to this quanta of energy h bar omega. Okay, just like the photon that has a description in terms of a quantum particle, and it's a particle that is characterized by having some quanta of energy, h bar times frequency. Just like the photon, here we have something like that, some particle that has an energy h bar omega, and by applying the operator A dagger, you are creating it from the vacuum. If you apply the operator A on a state with n such particles, you are moving down in the ladder to n-1, which means that you destroy one particle. So there is an alternative description, whereas what I plotted here is the energy spectrum of a single particle in harmonic potential can occupy any of these energy levels, okay, and these will be eigenstates. the same states can be interpreted in a many-body language. Okay? So again, here we have a single particle, okay? Single particle, many energies. This problem is equivalent to a problem of many particles, single energy. Okay, so what do I mean by that? I first of all take the ground state and I give it another name. Now I call it a vacuum. Here it was called ground state. It has the property that it is the lowest energy state you can go, and there's no way you can go below. There's nothing below. In the new description, this ground state becomes a vacuum. It becomes a null state, if you like, above which I have one and only one energy level. It's h bar omega, okay, above the vacuum. Let's think of the vacuum as 0, and this is the energy h bar omega. But on this energy level, I can occupy as many particles I want, okay? And I'm actually inventing a particle. What is the particle? It's just a quantum of energy, okay? So for example, if you look at the state E1, E1 is the state that you get. Okay, sorry, this is state 1. Okay. It's the state you can get from the vacuum if you apply a dagger only once. Applying a dagger only once in my many-body language is putting only one particle here. Okay, let me actually separate it into three different cases, okay? So first of all, if in this picture, if the particle is in the ground state, you are in a vacuum. There are no phonons. Now let's give them a name, okay? These particles, I call them phonons. Okay, in analogy with photons, why phonons? Just because if you're thinking of quanta of, basically these are quanta of harmonic vibrations, okay? So they are sound waves, okay? That's why the name is photon. So here there's no photon, it's empty, okay? So this is the state, the ground state, 0. The state 1, where in the single particle language, it's just occupying the first excited state. Here it's going to be occupation of a single phonon, and the state 2, to get it, you have to apply a dagger twice. Then here you have 2 particles. Okay? And you can go on like this, and you can apply a dagger 17 times, you get 17 phonons. And they're all identical particle with energy h bar omega. And these particles are in fact the convenient degrees of freedom in terms of which we describe our system. Okay? We no longer keep track of the mechanical matter from which it's made. We're talking about vibration modes, and these vibration modes have particle character in terms of these new particles, which I call phonons. Okay? Now, notice that there is a special property of these particles. What can I say about them in terms of quantum statistics? They are bosons. Why? Because just by definition, I can occupy as many particles as I want in a single quantum state. There's only one quantum state. Okay? So this is an example of a system where you can convert a single particle with, as I said, a spectrum of infinitely many energy levels to a many-body problem, but in this many-body problem, there are infinitely many particles, but there is only one quantum number, okay? And that's associated to this omega. Okay, for each omega, you have one type of problem. So when I write the Hamiltonian like this, I already represent it in terms of the new degree, the emergent degree of freedom that I just defined. Okay? And I get used to the fact to think about it as a particle. Okay? And it's a particle that is a boson, and mathematically, the fact that it's a boson is, and we're going to discuss it in more detail later, is encoded in the fact that it's the commutators of the annihilation and creation operator is one. Okay? Okay. Okay, so that was all reminder of undergraduate physics. What do we have now? In our problem, we almost have the same thing because we have something that reminds very much of a harmonic oscillator. In fact, among the sum over k, there is one k that k equals 0. For k equals 0, well, actually, for k equals 0, you get nothing. Okay, so maybe that's not okay. That doesn't. It's not helping. So there's no such. I mean, there is such state, but it has zero elasticity, and it's not. It doesn't have. It's not really a degree of freedom. But what we have here is almost the same form of harmonic oscillator, except that the way we've written it, we have here non-Hermitian operators already at the level of a coordinate and momentum. Okay? But otherwise, and soon we are going now to define creation and annihilation operators of new emergent particles or phonons in such a way that they will take into account this complication of the k minus k, but they will eventually behave just exactly the same as in the single particle case. And in our Hamiltonian, we don't have just one k or one omega, we have many. So we don't have just a single harmonic oscillator, we have infinitely many, but they are independent because the Hamiltonian is just separable to different modes. Okay? So let's see how we do it systematically. Okay, now I'm erasing all that. And it's not very good. one, sorry. Okay, so let me now define. First of all, just like the way I did for the harmonic oscillator, I define a length scale that I call Lk as the square root of h bar over m omega k. Okay? Where omega k is again what I got here. It's a linear dispersive frequency related to wave number k. And in terms of this length scale, I now define an annihilation operator AK in complete analogy to what we did for the single particle harmonic oscillator, but with only slight modification. So this is phi k plus I Lk squared over h bar, and now in the single particle harmonic oscillator we had phi k and we had phi and pi. But here, remember, phi and pi here are not Hermitian, so I put here pi of minus. Okay? Phi of k and pi of minus. Okay, and therefore, AK dagger, let us now do it very carefully. What is the dagger of this operator?
It's F minus k.
So it's phi of minus k, right? Because remember that the conjugate of phi k is phi minus k. And here I have another I, so I have to put a minus sign. I Lk squared over h bar times pi k, right, great, exactly. Okay. And that's it. So that's a well-defined thing. And now what do? I take this, and you can always, of course, invert the transformation to get phi and pi in terms of A and A dagger. You plug it into here, and what do you get? Can you guess what you get? I think you can guess, without doing the calculation, that you're going to get sum over k times h bar omega k AK dagger Lk plus F. And if you don't believe me, do the calculation. But it comes out very nicely. Okay? So the Hamiltonian looks like exactly like a sum of many independent harmonic oscillator. Each has their own frequency, okay? And the operators AK and AK dagger obey the following commutation relation. AK and AK prime, because now AK prime dagger, sorry, because there are many K's and I can compute the commutator of each. What are they giving me? And remember that phi k and pi k prime are a delta, right? So this will give me exactly delta k. And there's another thing that you can show directly, and here it's a bit less trivial than the single particle case. What is this?
0.
This is 0, and of course, if this is 0, it's also true for its dagger. So I put dagger on both of them. It's also 0. Okay, great. So I have here operators that describe some bosonic particles. We know that they are boson just because we learned from the harmonic oscillator that you have no Pauli principle. You can occupy as many particles as you like in the same quantum state. And we get a set of algebraic equations. And therefore, I know what are the eigenstates of this Hamiltonian. I can just immediately tell you what they are. What are they? I mean, just knowing from the example of a single harmonic oscillator. So if you like, this is a free gas of harmonic oscillators, okay? The modes are independent, and therefore, the wave function is just a simple independent product of all of them, and I can write the most general quantum state, eigenstate of this Hamiltonian. I can write it as nk1, nk2, blah, 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 which I define in a minute. Okay, it's a product of certain ki states. Okay, and there can be, this can be only 2 or 16 or 100. It doesn't matter. I mean, you can basically think of it as if you have in your system, you have a set of particles. Each of them has a different quantum number. And each quantum number you can occupy with as many bosons as you like. Okay? So let me give you an example, a simple example. So if I'm writing a state like this, okay, so I have h bar omega k1 and h bar omega k2, okay, and I have a state where here I put 1 particle and here I have 2. Okay. And similarly, I can put here 3 and 7, so here I have 3 and here 7. So I can imagine a state with, I can decide how many phonons, I want to occupy in each state. Maybe 0, maybe 10 to the 23. But if you want formally, how do we write it? We can write it as a product over all these quantum numbers of, sorry, don't confuse this with the operator pi. Here it's a product, okay, capital pi, of 1 over n ki factorial square of a ki dagger to the power n ki, all that acting on the vacuum. Okay? That will be a state where literally describes, you apply the creation operator of each k state, nk times. Okay? And you have a simple product of all of them, and this, if you apply this Hamiltonian on such a state, what will you get? What will be the eigenvalues? Okay? it will be just the sum over k, h bar omega k, nk plus half. Right? Okay.
It's not that accurate to write it like this.
Sorry?
It's not that accurate to write it like this, because here you said that the Hilbert space that you're acting on is 2. Or, I mean, you have 1 Hilbert space. It
What
should
do
be
you mean?
tensor product.
No, the Hilbert, so actually, thank you for mentioning. What I wrote here is that the set of all states that can be written like this
Okay.
is the Hilbert space. Okay, so the Hilbert space here allows for any occupation of any of the k states that are represented. Okay? And the states are actually characterized by 2 things. First of all, they are the quantum numbers k. These are your allowed modes, okay? Whatever they are, right? Which depends on the boundary conditions or not. They can be infinite. And for each of them, you can put here any integer, actually any positive or either 0 or a positive integer. And any combinations of n's here defines a state, and your Hilbert space is this set of sets. Yes, right? And in fact, you can think of superpositions of them. Okay? But each of these states is an eigenstate of the Hamiltonian with a well-defined energy. Yes? Yes?
In principle, K is can be arbitrarily large, right?
Yes?
But if that's the case, the ground state is infinity.
No, the ground state is the ground state is a state where there are no phonons, 0 phonons.
Okay, but we still have the second term in the Hamiltonian.
Yeah, but okay. What do you mean? No, but that's not interesting. It's a constant. You're saying that it can be infinite.
Right.
But it doesn't matter because it's. You're right. Right. But I mean, if you really have in the thermodynamic limit, you have infinity, but this infinity is not. So actually the value of the constant or the ground state, the value of the ground state energy is of no significance because all the physics is in the excitations above the ground state. Okay? So it's there's some energy, you can call this 0. You can define your physical world in the many-body language to be anything that is above the vacuum. Okay? And the vacuum you can think of infinite universe as your vacuum, if you like, right? What is the energy of the empty universe? I don't care. I don't know and I don't care. Okay? Right? I care about the energy of particles. Okay? And these are my particles. So there is so the state 0, 0, 0, 0, 0 is, now I'll give it a name, it's a vacuum. Okay? Let me write it down. Yes, which is what I wrote here. So this is called a vacuum state, okay? And it is nothing but a reference state above which I'm creating particles by applying creation operator, okay? And it satisfies, and that's very, very important, for any k, ak acting on the vacuum gives you 0. Okay, so there's the set of operators ak are set of operators that annihilate the vacuum. Okay? All right. Okay, so this will be so we saw that in this example, yeah.
What happens if, for example, you have the state 1, 0, and the operator A2 acting on it? It's also 0 because it's not a vacuum. You still have one phonon in K equal 1.
Sorry.
You have like the state 1, 0.
Yes.
And you're applying A2 in this state.
A2, and then you are creating the particle in state K2. Yeah. So you're saying if I have a state, let me call it, this will be K1 and this K2, one, or you wanted the opposite.
Yeah.
Doesn't matter, okay? This, okay?
Yeah.
Okay, and now what is the question?
Now you're applying AK2. Yeah, 0.
AK2 on this?
Yeah, is it 0?
I
It's
get
vacuum?
0. Yes.
Okay.
It's undefined. I mean, this zero is just undefined. I mean, the meaning of the zero is undefined because we are going out from this Hilbert space that we defined at the beginning. It's just a node.
No, I don't.
Because I mean, here we are ignoring the fact that we have also a photon. I mean, the creation is coming from something. Also, the annihilation annihilate something.
No, but the Hilbert space is the set of all states where n of any k can be anything from 0 to infinity. Okay? This is the Hilbert space. There are some operators that in this Hilbert space have 0 eigenvalues. Okay? This is a simple example of that. Okay? So yes, you are right. You in order to get zero eigenvalue, you don't need not only the vacuum. Okay? There are other cases, but yeah, okay. There are other null operators for specific, but then in this case it will be only AK2, not AK1 or okay, or actually AK3 will also give you 0, right? Right. So yeah, I mean, if you like. To do the bookkeeping correctly, you want to include all the possible Ks, but many of them can be 0, and that's a legitimate state. Right? And it is such that some operators give you 0 when you apply, some not, depending. So in fact, any combination of A's and A dagger can give you something. Some of them may give you 0. Okay? Okay, so this is the description, and you see that we basically replaced our elastic medium, our description of the elastic medium, starting from a field theory. We reached to a particle description. But we had to define some emergent particles, and we call them phonons. And they have energy h bar omega, where omega in our particular problem is a linearly dispersing wave. And it has the following property that when you go to the limit k goes to 0, what happens to omega? It also goes to 0, right? So the spectrum of the phonons in our model is simply linear, right? This is the dispersion. And actually, if you remember from solid state, I mean, it's not the first time you hear about phonons, right? In solid state, we discuss them as crystal vibrations. And if you remember, there are 2 types in principle of phonons. And one of them is the acoustic phonons, and they actually exist in any crystal, including a single atomic crystal. And this is exactly what we get here. This is a dispersion of acoustic phonons. Remember, we had a one-dimensional problem, and we can also notice that the phonons there's another property, they are also longitudinal, because the vibrations are along the direction of the wave vector k. And we can also think of transverse phonons, and they can also be quantized in such a way, they have different frequencies. And if you have a crystal more complicated, like a two-atom chain or something like that, which is not a Bravais lattice, then you're also going to have optical phonons. The optical phonons typically don't have such dispersion, you remember? So they cannot be described by this theory, okay? In fact, to get so you can write an analogous theory that will give you a Hamiltonian similar to what you get for optical phonons, but it will need to have another term, which is a mass term, okay, or some constant. So if I add here a term that is just a constant times phi k, phi squared in the original Hamiltonian, just phi squared times a constant, then my omega is going to be C plus some, okay, something like that. Okay, actually, this is what you're going to find. Okay, and this is the dispersion of, typical dispersion of optical phonons. In your homework exercise, the first homework exercise, you will see such example, which is an extension of the original field theory. Okay? But the principle is the same. The principle is that in the Hamiltonian language, you get something that you can write as a sum over modes, and you have some harmonic oscillator form, and the omegas are, maybe they have a different dispersion, but the idea is the same. Okay? Okay, so so one additional thing we can say about these phonons is that this dispersion also describes, it describes the relation between frequency and wave number. But if we multiply both of them by h bar, just like in the problem of photons that you are, I think, already heard about and are familiar, h bar omega is energy, h bar k is momentum, and the energy momentum relation is linear, it's not quadratic. Okay? So what does this mean in terms of kinematic properties of the particles?
They move in constant speed.
They move in constant speed. The energy momentum relation is linear, it's not quadratic. So this is in special relativity, this describes particles with zero mass, zero rest mass. Okay? Okay? So these phonons are the acoustic phonons, unlike the optical phonons are, if you think of them in terms of kinematic rules for the particles, they are relativistic. They are massless particles. Okay? Okay. Yeah?
But V, it's not necessarily C, like just
it's usually not C.
Okay.
It's the velocity of sound, and it's typically, of course, much smaller. Yes, you're right. It's whatever it is. It's given by square root of rho s over m. But in like in typical materials, it's a few orders of magnitude smaller than just the velocity of light. But it's not really. It is the sound velocity. Okay. Okay. Yes, but you're right. So it's like doing it's like relativistic particle, but with the role of the speed of light being played by some other quantity, but it's just a parameter. Okay? All right? Okay. Great. So, this summarizes our quantization of the mechanical example of field theory, which is elastic vibrations in a string. But last week, we saw that in fact we can write Lagrangian and a field theoretical description also for electromagnetism. And I'm going to show you, today I will not finish, but let us at least start. I'll show you that eventually, if you just apply exactly the same rules, starting from a Lagrangian, going to Hamiltonian, defining momentum and coordinates in the same way that you do for the general thing, you're going to end up with an Hamiltonian that has exactly this form, with some more quantum numbers perhaps here. Okay? But it will, once again, give you something that you can write as a set of independent particles. In that case, what are the particles? We already know what they are. They are the photons. They are really the photons. Okay? So let's see how it goes about. The first stage is to write this is better. We want to write a Lagrangian for the electromagnetism. And last week we already wrote it, except that you still didn't see how you derive the coefficients and all that, but let me just remind you the result. We wrote a Lagrangian that looks like this. So it's like it. Where L is plus a term that couples to the matter field, to currents and the charge density. And now let us talk about in vacuum. Now when I say vacuum, it's not the vacuum of before, it's like the real vacuum, no matter, okay? Vacuum meaning J equals 0. The second term does not exist. And I just have F mu nu, right? Well, I remind you what is F mu nu. It's the anti-symmetric derivative of the vector, the 4-vector potential, where mu and nu are 4 indices, okay? Time and 3 dimensions of space. Now, usually, so unlike the problem of before, we start from many fields. We have a 4-vector and 4 derivatives and all the combinations. It's usually complicated, okay? But there is something nice about electromagnetism. We mentioned it last week. It has a gauge symmetry, right? So all the physics is remaining invariant if we make a gauge. We can always make a gauge, and therefore, depending on what is your purposes, you can choose a gauge that is convenient, and choosing a gauge reduces the number of variables. Okay? In particular, let us, for our purpose, let us choose the so-called Coulomb gauge. It is, so remember the mu, the four vector usually is 4 components, electrostatic and vector potential, right? And in the Coulomb gauge, I choose phi to be 0, and for the vector potential A, the divergence of A is 0. Okay? This is also called the Coulomb gauge, and it simplifies the expression a lot. If you use these constraints, I'm not doing the calculation, but let me write down the result. For the Lagrangian density, it's going to take the form. Let me see if there are factors of half, maybe. Yeah, okay, so actually it's 1 over 8 pi. Then that's all. Okay, so this is absolute value. Okay, so it's just the time derivative square minus the curl of A square. That's
just
all.
The electric and the magnetic.
Exactly, yeah, good. This was exactly the question I wanted to throw on you. Exactly right. The first term is what we call, is in fact just the electric field, right? Square. The second term is curl of A is magnetic field. So in terms of the good old electric and magnetic field, it is nothing but E square minus B square. And notice that what it reminds you of, this is like a kinetic energy, and this is potential energy, and I wrote here a Lagrangian density. If I go to Hamiltonian, what will change here is that the potential energy will appear in a plus sign, right? So the Hamiltonian will be just E squared plus B squared over 1 over 8 pi. This is what you are familiar with. By the way, I remind you again that I work here in CGS units, so E and B have the same units, and we're also going to assume C equals, for getting this, we assume C equals 1. Okay? Yes?
There's not supposed to be a minus in the Lagrangian before the A mu, J mu?
No. I mean, it's a matter of definition. No. Yeah. Okay. By the way, notice that A mu is defined where the space like is minus. Okay. That's cool. Okay, so basically the interpretation is very simple, and if you just look at the form, you notice that it's very, very similar. Okay, there are some complications because of the directions here. So here there's a curl and not just a gradient. Here there's a time derivative. And the A is a 3 vector. Okay? But otherwise, it looks like a very simple generalization of the Lagrangian we had for the phonons, right? It's something that has quadratic kinetic energy with a time derivative square of something. So for each component of A, you have a contribution that looks like very much like the mechanical problem of the harmonic oscillator we introduced before. I think it's easy to see that, I mean, if you can, if you view A as the coordinate, then the conjugate momentum will be the derivative with respect to the time derivative dt A, and it will be proportional to, so the electric field is in some way playing the role of a momentum up to a constant.
And again, there's a non-local term in the...
Of course, yes. And once again, in order to write it in a convenient way, we're going to go to Fourier space. But we have to keep track of the fact that both the wave vector, that before we just had the wave number k, now it will become a vector in 3 dimensions. And also A itself, and its Fourier components are 3-dimensional vectors. So I ran out of time. We'll continue it next week. But this is the procedure. I'm already telling you a spoiler. At the end, we're going to get something that looks a lot like the phonon, but the summation is over k vector, and in addition to k, we're going to get another quantum number that characterizes the direction of the mode of the A, okay? Because it's a vector, not a scalar. Okay, so we'll do it next week. Okay, so thank you, and at 6 o'clock, Sarah will replace you to Tolk.
Today is going to be a pretty simple tutorial. It's mostly revising stuff that you should have seen in the first degree. And we'll talk a little bit about electromagnetic theory and Lagrange theory, just a tiny bit. And if we'll have time, we'll talk about conservation law and where they come from. For example, why energy conserves, stuff like that, if we'll have time. My name is Saul Levin. I'm gonna write my personal phone number and email. I always give my personal details. And feel free to ask me any question. Right. 054-831-0711. SAR LV44@gmail. Again, ask me any question, but please don't send me any question of is this answer correct? Is this development correct? People done it in the past, and that's not the answer that you should ask. The question that you should ask. Okay, so let's start with. Right. So in electromagnetic theory, we know, I'll remind you the four Maxwell equations. We have two homogeneous equations, which don't depend on the current or the charge. And the gradient of B is equal to 0. And we have the two inhomogeneous equations. The gradient of the electric field equals the charge density, and the curl, the magnetic field, minus the time derivative of electric field is equals the current density. Right? This I don't actually remember how you get to this equation from electromagnetic in the course, but here we'll write them again, get them again in a different way. We see here that the electric field is composed of three quadratules, three degrees of freedom. So is the magnetic field. But we know that there's some sort of connection between them using the electric potential. So if I write the electric and magnetic field using the electromagnetic potential, I can write the electric field as being minus a gradient of scalar field minus time derivative of the vector field, magnetic field equal to the curl of the vector. So we can reduce from 6 degrees of freedom down to 4 degrees of freedom, the scalar field and the free direction of the vector potential field.
Is that the mind writing black marker? If they see it as well as home.
I don't know. That's the color I'm missing actually. So thank you. I brought a few colors, but didn't bring black. I hope my motor skills are good. No, not good enough. No problem. Oh. Okay. Using the potential field, we can already achieve the homogeneous equation. Let's, for example, take the first one that I wrote on the left side, the gradient of B. If we'll take the gradient over the equation for the magnetic field, gradient times curl is by definition 0, always. And you can do the same thing here. If you take the curl of the electric field, you get the top equation. But now, most of you should have seen that there is a relativistic physics in the first degree, right? I forgot already. All right. So you should have seen a four-vector type of writing, where we can define the four displacement vector. It's called x mu equal to t minus r vector. It's called the covariant vector. And we can also write the same thing with the upper index. T R. So this, with the down index we call it covariant. And when the index is up, we call it Contravariant. Thank you. And to connect these two vectors, we'll define also a matrix. Let's call it G equals to plus 1, 0, 0, plus 1, 0, 0, 0, 0, minus 1. Okay. And with this matrix, we can write for example, the contravariant is x top u x. Notice that while this equation, there's a vectors and matrix hidden within it. You can also look at it index, and also solve it like that. So it's basically all of this vector formalism is just to simplify big vectorial equation or big sums into very small neat packets, which fit very nice with the relativistic theory, with the connection of time and space. Okay. Back to electromagnetism, we can also define a 4-vector for our variables. We can define the 4 current. We can define the 4 potential. And the 4 gradient. The mu equals to t. Notice that in relativistic convention, the gradient, the covariance gradient doesn't have a minus. The sign is flipped, the gradient itself. Any questions so far? Also, don't be afraid to stop me, like while I'm talking or writing, stuff like that. Questions? Okay, now using this four convention, 4 vectors, I want to slowly go back to the left side of the field, very slowly, of the board. For that, we'll define a field tensor, electromagnetic field tensor. F u equals to do mu au minus do u a mu. Just to understand the formalism, let's try to, I'll give you a second to copy it, and let's try to find one of the terms. Let's try to find the term in the 0 column, 0 row, and first column. Notice that in the 4-vector convention we start from 0, 0, 1, 2, 3, so 1, 2, 3, 4. All right, so F01 be equal to dot T, the A1 minus dou X, A0, which is V. Right. If we'll take this term and look at the electromagnetic field equation, we'll see here a minus dot T of the vectoral field, a vectoral potential field in the x direction. So this one is an x minus the x gradient of the scalar potential field, which will just be x. Right. Overall, equal to, I'm just going to write type 3. You can check each term if you really like to. 1 minus 2, 3. Now I can also define the contravariant of our F matrix, of our F variant covariance matrix, by equal to 0 minus E1 minus 2 minus E3. E1, E2, E3, 0, E2, 1. Now there's a question: how do I get from the first one, the covariance, to the contravariance in a matrix? Do you have a question?
No, with the metric tensor.
Yeah, we can again use our G, the matrix that we defined to raise or decrease indexes, but we'll have to increase both indexes. So we need one matrix for the V and one matrix for the mu, the U for the mu. So U equal to G mu sigma G O F sigma. Yeah, we can. There's two ways to look at this equation. The first, and I think the simpler way, is just looking at it as multiplying matrices, which is still not simple, but it's simpler. Or we can just look at the sigma and rho term as sums outside of this line right here, and then we can find each term of the contravariant. So far, it's just formalism. Can I erase the middle one? I want to keep the Maxwell equation. Well, so now the first thing that we can do is try to get some derivative of the F contravariant matrix in order to find the homogeneous Maxwell equation. You see very simple that the homogeneous Maxwell equation just need the electric field and the the inhomogeneous. Just need the electric field and the magnetic field with some derivative. Very simply find that mu let's do one example here just to make sense of this equation. Let's try to find the electric field in homogeneous equation, homogeneous quantum equation. Let's take u equals 0, and now the 4 vector of 0 will be rho, and now 0 column will be this. So we need dou t f0 0 plus dou x f1 0 plus dou y f2 0 dou z f3 0 0 term is just 0, and then it's ex, ey, ez equals to x plus y, z, it's really just the gradient. Do you need another example to? Okay. So now we'll talk about Lagrangian classic field theory. Can I erase this side? Let's say that I have some set of fields. Right, where I have n fields, so I go from 1 to n. I'll do it real quick because I'm sure you remember Lagrangian equation. We can write a Lagrangian density which depends on the fields I and all of the first derivatives. Okay. And by using this Lagrangian density, we can find the Lagrangian itself. The density of this one, the Lagrangian itself, we can find the action. All simply, the action equals the 4 integral of the Lagrangian density. Now by demanding the least action principle, we know that the solution will be the Euler-Lagrange equation. Mu of course, we have an equation for each field, and over here the 4 terms compacted in a very small way of writing. Notice that how I wrote it here doesn't leave one. You can really look at this as vectors because you have 1 divided by some vector, which is not really good. So in here it's just a convention of summation. Additionally, we can find the canonical momentum using the Lagrangian density by I equals n to and use the canonical momentum to find the Hamiltonian. I'm sure I don't have to say it, but the canonical momentum has nothing to do with the actual momentum. Hope you all remember that. And again, I'm going over the Euler-Lagrange equation and rules real quick because I'm sure you already know this. If you have a question, if you don't remember something about Euler-Lagrange, let me know. I just wrote it real quick so we'll have it in front of our faces. Alright. Now I'm going to give you the Lagrange of the electromagnetic field up to two constants, and we'll try to find those constants using the Euler-Lagrange equation and the Hamiltonian and energy. Right. We are given a Lagrange density. One u plus 2 mu j mu. Notice here that our field is the potential field and not the density, the 4 density vector. So overall, to get we have 4 different fields, 4 different elements of the 4 potential, and we need to calculate 16 terms. 4 terms for each direct derivative, and we have another 4 terms for each one of the derivative of derivative. And we expect, if we get the equation of motion, we expect to see the Maxwell equation again somehow. Let's try it. Okay, so overall, because I already used u and u, in the Euler-Lagrange equation, I'm going to use rho and sigma instead. Let's start with a simpler term first. Both f's, as we wrote before, are derivative of the potential field. So the first term is ignored. And we just have the C2 A mu, J mu, rho, A rho. C2 and J mu goes out. C2 J mu. A mu, dou of A mu divided by dou of rho, just to be a delta function. So equal to C2 J. Now, in order to find the next term, we need to isolate all the terms which are dou rho a dou sigma a rho. We notice that in the f mu u up top, that the indexes are above, not below. Let's write it explicitly. minus u I'm going to continue from here. Minus u mu dou mu é u plus dou u mu dou now let's remember that the mu and u are just random, just indexes. They don't have any meaning. So I can replace the lower half, the terms u and u, one another, and combine these two terms and these two terms. For example, let's just look at it. For example, let's say first I look at mu equals 1 and u equals 1 equals 2, just so that they'll be different. So it'll be 1, 2, 1, 2, and the last term will be 2, 1, 2, 1. But later on, I'm going to have to also sum over mu equals 2, u equals 1. And then the last term will become 1, 2, 1, 2. Just like the first term in the first segment. Overall, 2, 3 minus 2. The last transition, do you understand the last transition? Do you have a question? It's a bit sub-short. Okay, so we open up the equation here and sort of organize it a little bit, and now we just need to lower the indexes. So for each one of the 4 terms, do mu, do u, a mu, I'm going to multiply it by a different g, so that do mu equal to u alpha to alpha, basic a beta beta, do u g u beta do beta mu equals to u alpha a alpha. In addition, I know that G is a diagonal matrix, so I can take it to the side, the outside. So F UU UU equal to 2 G alpha G U beta dou mu AU alpha beta minus 2 G beta G alpha to Yeah.
It doesn't matter even if G is the diagonal matrix, because since you are operating with indexes, you can move it around. You're only, those are scalars, right?
Yeah. Oh, also true. Yeah. Yeah. That's also okay. Technically, we can also make it a little bit quicker if we just reduce the terms here. But I want to do the entire thing. Yeah. But good catch. Okay. So now we have only terms with the lower indexes, only covariant, and we can find this term. I heard that. Alright. I think we're gonna have to say bye-bye to Maxwell equation. So sorry.
Okay, we remember them.
You always remember them in our house. מה להיות החדר? She's in my lab, so she should be careful. Sigma in row. Alright. First of all, there's a 2 over there, and a C1 over here. 2 C1. And row of right again. Alpha. Okay. This will have 4 terms. One deriving the first term, one deriving this one. You know how to do the derivation yourself. To C1 G. Okay, I will also take the G outside. Just to make it quicker. G alpha, G beta. So, first of all, the delta. Delta sigma mu delta mu alpha beta plus do sigma alpha u minus delta rho u yeah. Alright. Just need to activate the deltas. To use the deltas, get equal to C1 G. Beta do alpha beta plus G mu G. Oh, so long. Don't worry, everyone. There will be longer calculation with this course, much longer. Roll down. Minus okay. So now just moving the indexes back up using the G's. So for example, G rho beta will work on A beta, move the beta up and transform it into a row. We'll get for C1 is sigma sigma A row minus sigma row the row. All right. This right here for C1 F row C. And the Maxwell equation at the end will be C2 J rho minus 4 C1 rho sigma F sigma rho 0. Or if we organize it a little bit, dou of sigma rho equals to C2 divided by 4 C1 J U rho. And we saw earlier when we formulated the electromagnetic equation, we saw this equation earlier with an index of 1 here. So we know that C2 equals to 4 C1. So now we only have to find one of these. We only have one of these left. Of these constants. Do you want a break in the middle or no? No. So we'll now find C1 by taking the Kanji equation, saying okay, we're working in the vacuum for a second, and trying to calculate the known energy of an electromagnetic field in vacuum. Which I'll remind you, m to 1/2 dq d squared plus in order order to find the energy using our Lagrange equation, we need to find the Hamiltonian. In order to find the Hamiltonian, we need to find the canonical momentum. All right. I'm going to write the 4 canonical momentum as Lagrangian, 0. All right, but we already calculated this term earlier, right here. We just need to put a 0 in our row. Let's stay consistent. Right? Just be 4 C1 F0 rho. Right? And we know the term F0 rho should just give us pi 0 equal to 0, by I equal to minus 4 C1 ER. Now that we have the canonical momentum, we can find the Hamiltonian itself, the Hamiltonian density. By mu 0 minus before I finish this equation, I would like to find a simpler representation of L. C1 with U minus so be equal, we need to sum over every different number here, and over every mu and u. And if you remember correctly, I'm just going to write the. I'm not going to write the matrix again, it's too long. Basically, you will remember that the difference between these two matrices is that the electric field will have a minus sign between them. So the magnetic field will just get squared, and the electric field will get a minus squared. So overall will be 2c1 minus squared plus squared. You can test me if you like. Next, the second part of the Hamiltonian, pi mu dou 0 a mu equal to pi 0 dou 0 a 0 plus 4c1 ei dou 0 ei. So we see that overall, this entire equation will just be equal to 4c1 e vector to 0 e vector. So the Hamiltonian density overall So 1, E vector, dot 0, A vector, plus 2, sig1, squared, B squared. Notice that I took the minus from the return equation and put it inside the bracket. Now, I'm going to do a little trick. I'm going to add the missing terms here in the derivative by adding and subtracting 2 E vector gradient 0. C1 E vector 0 E vector plus 2 E 0 minus 2 E 0 plus squared minus E squared. And we can use the definition of the electric field minus E 0 minus 0. Right. So these two terms together is just be the electric field with the minus. So this is 1 minus 2 E squared minus 2 vector 0 plus square minus B squared. Coming short, if I just show it up, I can subtract this. It's until 7.5, right? Good time. Okay. Let's take the overall H already. H equals integral to the field R minus 2C 1 2. Oh, skip this. Now, because we don't have any density, we know that the gradient of the electric field is 0, and this term, the minus 2 vector, you can do integration by part, take the gradient outside, because one of the terms of the integration by part cancels out. We get less. We get 2 minus 2 E times. Now I can take the H. minus 2c. I saw that you already saw it in class, but I'll say it again. If one integral is defined up to a constant, and a two integral can be defined up to a line, an integral cube can be defined up to a surface term. Because we have a derivative here over some function times a cubic integral, this will just simplify into a surface integral. So we can remove it. You also saw it in class, right? When I walked in, I saw Efrat write something like that.
It should not be minus.
Yeah? Yeah. So this term cancels out. It basically it's like saying up to a constant. And we just get minus 2c1 q squared plus b squared. And you see here that the constant before the integral need to be half. So c1 equal to minus 1 divided by 4. And by that c2 would be minus 1. Alright. I'm going to start the next material in a second, but we'll probably not finish it. It will still be in your homework. And if we will not finish it, we'll finish it next tutorial, and the homework will be, instead of for 2 weeks, it will be for 4 weeks, because we might not finish the next part. So now the cool part. This was just remembering the math. We know that in our universe we have some constant variables overall. For example, energy is something that's conserved, momentum conserves, charge also conserved, and we always take it as a known fact. But there is actually a way to prove that those quantities are conserved. All of this comes from symmetries. Right. The title is Symmetry Transformation and we'll start by specifically proving it for the electromagnetic field, and if we have time, we'll say what's the general way to prove this sort of conserved materials, these conserved quantities. Right. So, Gauge found out that the action of the electromagnetic field remains constant for, let's say, a four potential vector field up to a change of derivative of some function, arbitrary function, plus the mu rho. We found that if you do this transformation, S of a mu equal to stag of a mu. So let's try to, we know this S, let's try to find what's S star and see what comes of it. All right. So, Lagrangian density, as we saw before, is 1 minus half dou mu u do mu u minus mu u do u mu and minus a mu j mu. And now the shifted Lagrangian minus half do mu of do u do mu u plus rho minus mu u plus rho do u a mu plus do mu rho minus AU plus do rho JU. Okay. Just rearranging the terms a little bit. If you have a question, you can ask me. It's fine. This one's gonna be long, so hold tight. Need a small ball to just copy paste it. So, right. Now, you'll notice that do mu do u rho equals to do u do mu of rho, and there's a lot of terms here that can cancel out. For example, this term and this term, so on and so forth. Overall, if you switch the derivatives and whatnot and do all this too long to write stuff, we'll get Lagrangian, new Lagrangian, equal to old Lagrangian, minus the rho G. That was the entire change. So Lagrange promised us that the difference between the two actions will be 0. So we'll just write it down. S minus S tag equal to derivative, the normal Lagrangian density move, derivative d4 of x of do mu of u equals strict conservation energy is equivalent to time scale, which I don't have a figure at time, but you can see it in the tutorial. Which gives us, actually this is something that I really like, that in the beginning of the universe, in the Big Bang, there was no energy conservation, because there was no time scale. You see the anti-symmetrical creation of both matter and anti-matter, which is why we have more matter comparing to the amount of antimatter. Let's see if we can do one more. I'm going to think real quick. Motors. Let's start with the most simplest case. We have one field phi x in some 4 vector. The x is some 4 vector that define our field, and we'll make some infinitesimal change in the field. A very, very small change. And we'll assume that this small change in the field will also induce a very, very small change in the Lagrangian. So the Lagrangian go to 2 plus alpha delta Lagrangian. Now, because we know that the Lagrangian is dependent on the field and this first derivative terms, we know what is this small change in the Lagrangian using Taylor series. In order to delta L, we have to be the of phi plus mu phi now. If we integrate this term by parts, and use this term right here, and use the Euler-Lagrange equation to simplify it. This term right in the beginning, we can simplify the entire delta L equation. the second term here will just be 0 for my Lagrange equation. We will just be left with mu go okay. So now the statement itself of the theorem. Okay. The statement says if we have a change by up to something that's equivalent to a 4 derivative of some general function mu delta s this small change, as we saw before, will give us a constant delta s, or star equal to d4x time equal to d4l plus alpha d4x j mu. Right. The theorem says that the small change that we did in the field before mu just be this function. This is just putting in. This is just putting in the what's we found here. It's the small change of the L. And using this equation, we can define the no term called what we call the Noether current by integrating both sides. We get define J mu x b dou phi this mu. And to obtain continuity, all of this makes sense, we must take J mu x, derivative of J mu to 0. And our conserved charge, according to the theorem, will be Q equal to integration of J. So there's a lot of self-referencing in here, but the theorem itself is very simple. You have a small change, find the change, find how it affects your field, and then find how it affects the Lagrangian, and just put everything, this equation. Just basically an equation to tell you what is the answer. I won't have time for the example. It's simple, but I will go over the example at the start of the next tutorial, and you can also read it at home. It's not that complicated. It's just the formulation seems complicated, but when you see it in the example, it's much simpler. I just don't have the time. You have just time. So this is the end. You may מרגש אותי. Right. Thank you everyone. Next class we should start doing some actual quantum. Very good. טוב, זה לא... אני אגיד לך את האמת, זה חומר למבחן. אנחנו נחזור קצת לאוילר לגרנד שנלמד תורת תורת הקוונטים, אבל זה לא ייראה ככה. זה ייראה יותר גרוע. זה כל זה.
יש לי שאלה, אולי גם נתפסתי כי חשבתי על פרופ אינדקסים. פה לא אמורים להיות הפכים, אם אני רוצה לעלות.
סתם, אתה מעניין.
אני למעלה ושם לפי המיעוט כאן.
שים לב שתגיע לדקה.
אבל איך אני עדיין אעלה את זה? כאילו גם הם מופיעים כמו שמופיעים כאן, אבל כאן המטריקה.
שים לב שהפוינט, בסופו של דבר, יש לך